So today, we're going to go deep, deep inside the engine room of a massive ship. We're going to pull back the curtain on the hidden network that keeps these absolute giants from, well, melting down. It's a story of incredible heat, some seriously clever engineering, and how the lifeblood of the ship interacts with the lifeblood of our planet, the ocean itself. Okay, just think about this for a second. A modern ship's engine is an absolute monster. It generates a terrifying amount of heat. We're talking temperatures that can literally warp and melt the very steel it's built from. So how on earth does this floating city, this powerhouse, keep its cool when it's hundreds of miles from anywhere? Let's get right to the heart of the problem, which you could call the engine's fever. You can think of the main engine as the ship's heart, right? It's beating with these incredibly powerful, fiery explosions. But with every single one of those heartbeats, it creates a wave of destructive heat that has to go somewhere. So to solve this massive heat problem, engineers basically took a page from biology. They gave the ship its own circulatory system. It's a whole network of pipes and pumps that act just like veins and arteries. And it has one primary job: to carry that life-threatening heat safely away from the engine. And the core idea, as you can see here, is actually pretty simple. You've got a cooling liquid, usually fresh water, that runs through passages inside the engine, just soaking up all that crazy heat. That now hot liquid then gets pumped to a device called a heat exchanger, and this is the magic part, where the vast, cold ocean is used as the ultimate radiator to cool the liquid right back down so it can start the cycle all over again. So that's the principle, but how do you actually apply it in the real world? Well, the first and most straightforward method is what we can call the direct approach, and the logic is pretty simple. Why not just use the endless supply of cold ocean water the ship is already sitting in? And this diagram shows that direct system perfectly. You can just follow the arrows. Seawater gets sucked in from the hull, pumped directly through the coolers to pick up the heat, and then shot right back out into the sea. It's effective, it's simple, but there's a huge catch. Pumping corrosive, salty, gritty seawater directly through your very expensive machinery is, over time, a recipe for disaster. Right, so to protect the engine from all that corrosive salt water, engineers developed a much smarter, more advanced approach using fresh water. Let's take a look at how this inner loop makes for a way more robust design. And here it is, the two-circuit system. And honestly, this is a total game changer. You've now got a closed primary loop of treated fresh water that circulates inside the engine. This is the stuff that actually touches the important parts. Then you have a completely separate secondary loop of raw seawater. Its only job is to cool down the fresh water from that first loop. So the piece that makes this all possible is that heat exchanger we mentioned. This is where the hot fresh water and the cold seawater pass right next to each other, separated by a bunch of thin metal plates. Heat literally jumps from the hot water to the cold water, but, and this is the critical part, the two liquids themselves never, ever touch. This is what protects the engine from salt and all the other gunk in the ocean. Okay, but a modern ship has way more than just one big engine to cool, right? You've got generators, air compressors, refrigeration systems, the list just goes on and on. Trying to manage separate cooling loops for everything would be an absolute nightmare. This is where you need a master system. And that brings us to the top of the food chain in marine engineering, the central cooling system. Now, as you can see from this diagram, yeah, it's a bit more complex, but the idea is brilliant. You have one big, highly efficient freshwater loop that acts as the main artery for the whole ship. This main loop gets cooled by seawater in a central heat exchanger, and then it branches off to serve every single piece of equipment on the ship that needs cooling. It's a much more elegant and efficient way to run the whole show. So we've seen how these systems keep the ship alive by moving huge amounts of water around. But here's the thing. This whole process doesn't just exist in a bubble. Discharging all that water back into the ocean, well, that brings up the really critical topic of the ship's environmental footprint. These cooling pipes are just one part of a huge network connecting the ship's guts directly to the marine environment. And this mind map is a fantastic way to see just how complex it all is. I mean, look at all these systems. You've got the cooling systems we've been talking about, sure, but also bilge water, ballast water, fuel systems, compressed air. Pretty much all of them are vital for the ship, and almost all of them interact with the sea in some way. So this brings up a really, really important question. With all these different fluids being moved around, processed, and sometimes discharged, how do we make sure a ship doesn't turn into a big source of pollution? What are the rules of the road? So how is all this managed? Well, the answer lies in international maritime law. And to really understand how it works, let's just do a little case study. We'll focus on one of the potentially dirtiest systems on board, the one that handles all the oily water.
This is the bilge system. It collects all the oily wastewater that drips and leaks in the machinery spaces. Now, to prevent pollution, this system is governed by a super important international treaty called MARPOL, and the rules are very strict. They follow a clear three-step process you see here. First, you can't just pump this stuff overboard. It has to be treated in an oily water separator. Second, the water being discharged has to be constantly monitored by a special device. And third, the big one, that discharge is only legal if the amount of oil left in the water is below a very, very precise limit.
And that limit is less than 15 parts per million. Let me say that again. 15. To put that in perspective, that's like finding just 15 drops of oil in a million drops of water. It is an incredibly tiny amount. But what does 15 ppm actually look like in the real world? This chart makes it really tangible. At less than 15 parts per million, the water you discharge leaves no visible trace, no oily sheen on the ocean surface. But the second you go over that line, you start to see and even smell that classic rainbow sheen. Get way over 100 ppm, and you're creating a full-blown oil slick. So the whole point of that 15 ppm rule is to ensure there is zero visible pollution, period. And so that kind of brings us full circle. The circulatory systems that are the lifeblood of these ships are true marvels of engineering. But we've seen that the regulations governing them are just as important, making sure that the ship's lifeblood doesn't poison the lifeblood of our planet. And that leaves us with one final crucial thought. As our ships and our technology get more and more powerful, how do we make sure our sense of responsibility keeps pace?